forward to your talk.
Sure. Thank you. Okay. Thank you. So I think, maybe you have to be 15 more minutes patient with me, so we're going to shift the whole thing, if you don't mind. I was going to go over an hour because I saw 75 minutes. So, and I progressively get louder. Don't worry about that. So I want to go back to my memories at Pitt and my years at Pitt, and say a few words about my years at Pitt. In fact, I came here in 2001 as a religious refugee. I was not a student. So first thing I had to do before I get to Pitt, I had to find a place to work. The place was not Pitt, was across the Pitt, was in the original hot dog shop. And that work lasted 3 days before they fired me and said, "Look, you don't understand English." So that was end of the work. And I was going around and try to get Pitt. I was good in physics and math, but I didn't have a job or anything. So I found a friend. Peter listened to my stories and became friends, and this is one communication. Peter was in charge of semester at sea, and I apparently wrote something to him, and he wrote back and sent this card from Osaka. I had to go through my stuff and find this card. It's very dear to me. And then he listened to my stories and said, "Oh, okay, it seems you can do physics and math. I help you to get in here." And then after one semester in community college and working with work similar to this, I got in. And then Peter said, "Well, look, you're good, but I don't have money. I like you, but I don't have money." Then he introduced me, and he took me to a man which was like no one else. Dean Alec Stewart. Dean really supportive and helped me, and then with Alec Stewart, we helped me to write the proposal or application for Barium Goldwater Fellowship. A year later, I got the Barium Goldwater scholarship. At that time, it was $15,000. It could cover the tuition at that time. I don't know how much you guys jacked the tuition these years, but it was very good enough. And I became a happy person. But I want to tell something about my years. I came as a very arrogant person because I felt like I can do way better than Pitt, right? What's this public school or semi-public school? But then it was very humbling years when I start to take classes and courses. And I realized, well, there's lots of things I don't know. The reason I came to Pitt is I had no money, and my aunt was living in the city, and I came in here, and I had no money to go even explore US. So I came here, I got stuck, I had this kind of works, and then, but then I was like, oh, probably I can do better than this, but then I gave up, and then as I was taking courses, I realized, well, there's a lot to learn in this place. So academic and teaching and whatnot was very useful, tell me that, okay, there is a lot. And then I took a class in this very room with Shalon, and then I started working in his lab, and I worked in his lab for 3 years, and I was so panicked that if I don't publish, I can't get to any grad school, so working day and night, staying up after midnight at Shalon's office. At that time, it was 408 or 418 in Allen Hall. And we managed to publish 2 works together before I went to grad school. And I learned that, Pitt has many things to offer, classes and then research. So I was happy at the end, and I left Pitt very happily. But I left with one regret. In 2009, I came back for APS March meeting, and Shalon was, I met Shalon downtown in the APS. And then Shalon said, "Alec wants to see you. Why don't you go back?" I got busy. I immediately drove back to Princeton. I never met Alec, and a year later, Alec passed away. I wish I had seen him one more time. So my work at Google is on quantum simulation. There are many things about quantum information and quantum simulation that you can learn from company owned by my company called YouTube. So I leave that to you to go and do the YouTube job. But I would tell you from my experience, and something that is probably is less in YouTube and more in our business, some other aspects of the work. The whole business started from Richard Feynman in early 1980s. He said that okay, let me tell you a different introduction. Very soon after quantum mechanics was conceived and was formed, we realized that there are very hard problems in physics and chemistry that cannot ever be solved. They're very hard. This very hard have a better technical terms, but it doesn't serve anything to use that language anyways. So these hard problems could be there forever if we rely on our classical computers to solve them. We know that for sure. But then in 1980s, Feynman said that, well, wait a minute, we can use quantum system to emulate and simulate quantum systems for us. That was his vision, and it was indeed a very deep vision. And then he said at the moment, on that article, that this is a very hard problem. And indeed, he was right. 40 years almost has passed, and we do not have a quantum simulator. Why that is the case? 40 years, and there is no work on published literature whatsoever that cannot be done in MATLAB or Python, in few lines of Python or MATLAB code. Why that is the case? Okay, the reason has to do with something that I explained to you now. But anyways, after I get to this in a second. But after Feynman's thing, there was many ideas and many platforms can get born that how to do this. And there are these many platforms, like for instance, you can look into, and that's you can implement Feynman's vision on it. But I think the core of the Feynman vision is captured in this thing that I draw in here. The core of the difficulty is that when you scale up your system, you're making more and more qubits, your system gets bigger, you don't lose control over the system. And to stay straight, go up straight, that is what he had in mind. If you come back and bend down and you scale up, you have lots of qubits, but you don't control them, that is where we have been since dawn of condensed matter conventional experiments that we have been doing, studying aluminum and copper. That, of course, we know how to do that part. But I think the vision, the difference is this thing, that to be like a puppet master, I used this example several times today, to be in control of the system and move your qubits at control. And okay, we can, but why it's hard? The core of the difficulty comes that you also need to maintain the quantum coherence. The quantumness and controllability goes opposite of each other. You can isolate and have a good coherence, but when you connect, you lose your coherence. So that is why we still have companies and people investigating in it, and we are in business and we get funding, because it's a hard problem, and I think I give you some glimpse on why it's hard. Also, when you choose your platform, you got to be sure you can measure the correlations. You have seen these theorists, you talk to them, they want you to measure XZX correlation. They are not interested in total magnetism or so. They have tricks to figure out. You have to be able to use very weird correlations or things that they just pull out of the thin air and ask you to do. So your platform has to provide this capability too. And having all of them, it is a holistic problem, realized in one platform. That is why it's hard about making a quantum computer. And that is not in any YouTube. Okay, so this idea started gaining some momentum in the past few years, and people call it a quantum race, a race to have a quantum platform. And now you open the news every day. One day you see that, one guy started a company with ion traps, and he says that's going to be the winning case. And then another day you see that IBM is gearing up to make a quantum computer, lots of jobs and openings in there. Another day you see that Google hires my postdoctoral advisor. Another day you see that some people start to think time scale on where you're going to have the quantum computer, and is getting a another day you see that, one guy who moved out of academic is starting his own startup and raise millions of dollars and money and create a huge company. And then another day you see that, that is how the thing is going to supposed to look like. So some people are start investigating that how this quantum computer is supposed to look like, and giving insights, and then try to squeeze funny information from us. Okay, so I tell you a little bit about how we make quantum computers, or how we are trying to make quantum computers, and how our platform look like. So the idea in here is based on Josephson junctions. The idea that Josephson got Nobel Prize for his discoveries or his finding in 1970s. If you have two superconducting islands which are almost connected but not connected and separated by a thin oxide or a weak link, then the superconducting phase in here and over there, if there are some difference in the superconducting phase, then you would see you would get a current, superconducting current going for you. And then if you, so this would be essentially this kind of a phase and current relation gives you a nonlinear inductor. If you shunt this inductor with a capacitor, now you have an LC oscillator, which is nonlinear, and that's great. Why it's great? Because now you can address these levels individually as opposed to harmonic potential, which if this was linear, then the spacing would have been uniform. You don't have any addressability. Now you get nonlinear spacing and you get addressability. How do you make this in the lab? Or in the fabrication, you start with some inert substrate, piece of glass. In this case is a sapphire, is aluminum oxide. It's just something to be inert and clean and whatnot. Or you can clean very nicely. And then you start put aluminum on it, and then some technique of lithography, called lithography, you pattern some pattern in it, and here is the capacitance I have been talking, and here is the inductance over there. And then this is the junction. Junction is down in here. This is the Josephson junctions in here. And then this is a zoom in into the junction, which is the aluminum oxide, which you don't see, and then aluminum on the other way. Okay, let me pass some qubits around. We did this yesterday. It was very fun. So in this, so this is how the qubits come out of the fabrication. Would look like I glue it to a piece of plastic. This is before you dice it, and this is the chips that actually are nominally identical to these was used in the experiments I would be talking now. So you would see 9 qubits in row, and I would walk you through how these 9s look like. This is a thing, so you feel like you're really doing actual science in here. This is a chip wired in a box that you can see how actually it looks like before you put it in the fridge. And then, of course, the box would be aluminum to expel any magnetic fields.
It does this on the mirror side.
Huh?
On the mirror-like side.
Right. So, okay, can I have a second? So this is where the aluminum is deposited, and try not to leave a fingerprint here. I have a fingerprint of very famous physicist in here. Let's not add to that collection. Okay. So, what else? So this is for technically for more advanced. So if you want to take a nap, check your emails. I give you a few minutes when I go over this. I promised this to people yesterday. I just say it for a few minutes. Don't worry about it if you don't understand this. The fact of the matter is this LC oscillator model is very good in describing what the system is. And it really helps us to design it. It's as simple as that. Nothing fancy about it, the LC oscillator. So the Hamiltonian of the system would look like something like this. This is the charge degree of freedom. And this would be the flux degree of freedom. And it appears in the cosine. This cosine is the integral of the sine, is the nonlinearity I mentioned. You can expand this cosine up to some point. This is k squared plus kx squared plus x squared that you know from your course in quantum mechanics, harmonic potential. That's not fancy. But this higher expansion in the cosine is what gives that nonlinearity, which is essential feature you need to have the addressability I mentioned. This is, again, up to here. The potential would be parabolic, and further down you go, you have cosine, and you get this level of spacing changing, which is crucial. Okay. And then some rotating wave approximation gives you this Hamiltonian for this part, and then you go later on, these higher orders give you the the nonlinearity of the interaction. Okay, and now let's say you get clever and you figure out how to couple the flux into this loop to flux into that loop. That would lead you to hopping. You can put a photon here, it would jump back and forth, and this gives you the hopping term. Okay, so putting all this together, you get the Bose-Hubbard Hamiltonian that was missing from yesterday's discussion, how you get there. But essentially, that's how you get in there. And that's the Hamiltonian of the system. If you're into theoretical physics business, that's what you need to know, and you can ignore this. So let me tell you how you couple qubits. That's an important part of the business. It's important to couple them. The idea of coupling the qubits that we implemented is like making a variometer. Variometer is an object, are two coils that are inside each other, and then you can change the relative angle of the two coils, and then you see the current going in one loop can induce current in the second or not, depending on the relative angle of the axis. That's called variometer. I didn't know what's that was called before, but anyways, that's a very simple idea, right? There's an axis, there are two axes and one angle between them, and that sets the amount of pickup you have in the pickup loop. Okay, so the coupling scheme is implementation or analogous to that. You have one qubit, you have another, you put a loop between them. In this loop, you put a current in here, there's inductive coupling, induces current into this induces flux or current in that loop. They get coupled, okay? That you can go to your classical mechanics textbook and see you have two coupled oscillators. If the strength of the coupling is m, the frequency would split as with this relation, right? M over 2 of bare frequencies essentially gets shifted. Now I define half of this splitting as my coupling. And now I go back and I start to figure out if there is a current in here, how much currents put in here and how much over there, and try to relate this M to these individual components of the circuit, and I arrive at the coupling. So it says, relation for the coupling says that when the coupling J, defined in this fashion, is given by these parameters of the system. Note that one parameter is this delta. This delta is the phase, superconducting phase difference across these junctions, okay? What does it mean? Meaning that if I could manage to put flux into this loop, I can change this delta. Essentially, they kind of roughly go linear with each other. I can change this delta. And when I change this delta, I can tune my coupling. And that is very important in the controllability scheme of things that I mentioned in the beginning according to Feynman's vision. You need that control. So here, this axis is the flux into this loop. I put flux into this loop, and I measure the splitting or measure hopping rate or measure the swap rate, or any of these would point to the same thing. You can see as I change the coupling, as I change the flux into this loop, which changes this phase across the junction, you get positive and negative coupling, and I can do it fast. I'll get to that, and you can turn on and off the coupling between them. And yesterday we talked how to make this hopping complex, and there is lots of control over there. So that is how the coupling between the qubit is achieved, and it can be done in time domain. After you have done this, you have to put the thing in a fridge. So you sign a deal with a company, and then they make you their fridge a little bigger than usual. So this is the view of the base mixing chamber of a fridge from below. Before you put the wire in here, you can put about 22 wires, at least 27 wires, the current scheme into each port. So about 300 wires, 300 microwave lines can come into this, and that's roughly the size of the fridge, and then it operates at 10 millikelvin. So you start putting your stuff in here, like this qubit box that is going around. With more qubits, the qubit box get bigger, and that mix plate get really, really filled before you close it. And then if you really know what you're doing, you might manage not to heat up the fridge, but that's also a story by itself. Okay, the chip that is going around looks like this. So let me tell you all these components, all these LC oscillator business, how they are, what are you looking at? This is the chip, is a about 1 centimeter across. These capacitance of the qubits appear as these line segments of aluminum. And then you see lots of wiring, again, coming to control the states of the qubits. And then there is some wiggly line up there, is a lambda over 4 resonator, which is used to read out the state of the qubit. These figure 8 sitting on the side, infinity signs, are the coupling loop between the qubits, and that's how you control the coupling. And then some of these lines go to couple the coupling, and some goes to change the qubits. Right? So here's a little zoom-in view of it. This is the capacitance according to our discussion. This is the going through the readout capacitance, capacitive coupling to readout resonator. And this is the coupling loop that I explained, that variometer in reality takes a more complicated pattern. And these lines that you can see, beginning of them are essentially used to control the state of the qubit or drive the qubit. You need to have the full control over all the terms in that Bose-Hubbard Hamiltonian. And these are some features of the system, that the crosstalk between the loops and then coherence time of the system. So maybe this was too much detail, but if you really don't care, this is the Hamiltonian of the system that we're going to play with. Okay. Now, I want you to walk you through an example. Okay, you've got the qubits, you have the financial resources. What do you do with it? Or where are you? How far have you gone into this business? So I walk you through an example that probably with your knowledge of quantum mechanics, you can digest it. It's not that hard. So we invented a spectroscopy method. Okay, how do you make a spectroscopy method? We are interested to look at our system and know the spectrum of energies, eigenenergies. We want to read the eigenenergies of the problem. Okay. So I mean, the method is so simple that came to my mind. So imagine how, but then it had so many issues. I need to get help to get it to really work out properly. But you know, this is nothing just but the fundamental assumption, a fundamental postulate of quantum mechanics, that the wave function according to this relation, this is the expansion of the wave function in energy basis, right? You have an expansion in energy basis. Phi alpha is the eigenenergy of the eigenstate of energy, or Hamiltonian, eigens of the Hamiltonian, and eigenvalues are the energies. And then you have a phase, and you have a prefactor which comes from your initial states, and that's how its states evolves. And you look at it, it pretty much looks like a Fourier transform relation, right? You can imagine that this is like a Fourier transform. So the essence of the method is very simple. There's some details, I would not get into it, but the idea is that you record the evolution, right? You record the evolution of some observables. You have to choose the observables cleverly. And then you Fourier transform it, and the Fourier transform would tell you the energies of the system. There are some caveats here, which I covered yesterday, so I wouldn't repeat it again. But essentially, you put an excitation, you turn on the Hamiltonian of interest. That's what happened in this period of time. And then you start reading the observables. This is part of the readout scheme. And you read some observable, like, you know, what is the expectation of this Pauli operator at a given site, okay? And then you Fourier transform it, and you get the energies. Believe me, it works. So this is a simple example that, you know, this is you excite qubit 8, you record the observable for some time, and then you Fourier transform it, and you see a peak. You can be more confident by exciting other places, and then looking at and then add them up. And maybe I go back for a second. The idea, maybe the analogy would help you to understand what is this all about. You see, you have an object, you want to know the frequency, natural frequency of it. You can hit it and listen to it. And then you can record the signal and Fourier transform it, and the recording, the Fourier transform tell you about some of the fundamental frequency. And then you hit it again, and then you record it. And you keep doing this business several times, and then that would help you to essentially be certain or grow some confidence that you find all the Fourier modes of the system. So that is the essence of the method, but it takes a bit of engineering to get it to work. But that's what it is. So you find 9 energy peaks. You add these Fourier transform, and you find 9 peaks. And you say, OK, so the Hamiltonian has to have 9 energies. These are my energies. That fine, you can, but there are more peaks. Experimental, there are more peaks in the system, right? How do you know that this is what correct eigenvalue? So I walk you through an example so you can be confident, or I can tell you how confident we are that we can solve a given problem, right? Anything you add up of anything you fully transform, you can find 9 peaks in it. That's not surprise. How do I know this is not a peak? Okay, it was a smaller, but how confident I am. So the example would serve you in this purpose. So we picked up a, yes?
In the color plot, that one is actually not smaller. That one is red. And
Right, but you add them up. You add all these lines up. This is 9 things added together. Overall, at the end, it lost. You're right. So there is an example of a study of electrons in a magnetic field. I think this would serve as a good example of where we are in terms of control of the system and such. When electrons are going in a lattice, they are hopping from lattice sites, and they're also exposed to vertical magnetic field. There would be cyclotron motion length scale associated to magnetic field, and there would be a hopping rate. There are 2 length scale. When these two compete with each other, you get very interesting physics. That first time was solved, and the spectrum of this system was figured out by Douglas Hofstadter in 1970s. So that problem can be mapped into something called Harper-Hamiltonian. Somehow it get mapped there. Essentially, what I have done in here, this is like a magnetic field. And imagine you have 150 eigenenergies in this system. And I went to my computer and say, where are the eigenvalues of the problem? And for every magnetic field, I have 150 energies, and I put a dot. Okay, this is all done in my laptop, nothing fancy there. And this pattern have some fractal properties called, and has been studied to death, but it hasn't been realized in the lab. Why? Because the magnetic cyclotron motion dimension is way bigger for the magnetic fields we have on this planet compared to lattice spacing. These 2 length scales do not get commensurate easily. This is the ratio of the 2 length scales. And to explore this pattern, get this full thing in the lab, you need magnetic fields in the order of 10,000 Tesla. Okay, that's not going to happen. And in fact, this beginning of it is accessible. So people, when they had graphene layers, which has some super lattices, some more patterns, when there were bilayers which introduce a super lattice, then there was some chance to get the 2 length scale comparable with each other. And based on that, they measuring conductance. They see some feature consistent being with this butterfly. But keep in mind, this is a spectroscopy would reveal this, and they are measuring conductance. So they can see only consistency with this physics, not exactly probing the physics. So I set the goal that we're going to do it with our 9 qubits. The butterfly, all the beauty and fractal of it would be gone, but some ghost of it would be remaining. There's no fractal properties left in here. But if I change the magnetic field in 100 steps and with 9 lattice sites, this would be the butterfly, the ghost of it, the leftover of it. It has some butterfly looking to it. But this would be where I would get the points. Still, this is done in my laptop, nothing fancy yet. Okay? Okay, if you're ready, we're going to do this in the lab. We are going to do our hit and listen, the bell technique or whatever you guys call it. And then we're going to do this. We're going to change the magnetic field 100 times, and we're going to Fourier transform and read 9 tallest peak, call them eigenenergies of the system. And that is what we got in the lab. This is the Fourier transform of those signals that after we record them in time domain. So, okay, you can lock your eyes to some feature, I don't know, wherever you like, and we can go and see it. Oh, what did I do? Oh. Okay. And then you can see if the feature repeat. Sorry to hear. Okay, may I stop here? So you can see that if the feature repeats itself or not, or is a good match or not. So, but to do this more systematically, we went to every magnetic field that we set, we read the 9 tallest peak, and then compare it to what we expected it to be, where it expected to be. And the gray line is what in our computer we set to get. Okay, that was the theoretical prediction. The points, the dots, are where we found them in the lab. The color of the dots is how a dot is deviating from where it meant to be. For instance, if it's dead on, you get black, 0 error. If it deviates, you get yellow. If you're really missing, you get red. Okay, that's the color of the dot. If this was fully black, we're really in business. If it's getting toward red, we are not that good. So you can add all these numbers together, and then you can tell you the rough estimate of the control that we can do at our qubit. It involved controlling 17 knobs at the same time to achieve this pattern for every magnet.
Magnetic fields do you need for that?
Well, but you have to think about it the terms of the Hamiltonian. In the lab, I have this Bose-Hubbard, and I have been changing these B values where delta and J was set to 50 megahertz. So there's no, the problem from electron land got landed to this Bose-Hubbard language. I didn't go through that.
The analog of, what's this B?
Magnetic field. So when 1 is that 10,000 Tesla. This is the relation, huh?
What did you?
Here. Delta, this is the sigma z. This is the local detuning of the
But in the
qubit.
lab, you cannot get 10,000 Tesla. What did you change?
The local detuning of the qubits. You turn on the coupling to this value, J, 50 megahertz. You set this delta to 50, but how much detune every qubit, get this factor of cosine next to it. The first qubit would be by cosine of 2 pi b. The second would be cosine of 4 pi b. The detuning of the qubit has this cosine profile.
So does 1 mean 1 flux quantum per unit cell?
I think so.
In that
I
case?
think so. I think so.
Okay.
This is such a huge magnetic field that the cyclotron and right. I mean, you know better than me. Did I cite you? Did I?
1 flux quantum per.
Huh?
I would guess that 1.
Yes. Right. Yeah. Right. Yeah. I think so. Yeah. Right. So that's our first state-of-the-art work, or where we are now. See, this is error analysis of it. Okay. Going to the second part. So. If you go to open, I don't know, your favorite magazine, news, or whatever agency, you see they keep talking about this quantum supremacy. So I want to talk about that quantum supremacy for a few minutes, and then that's it. So again, this is based on one of our work, which is still on archive, but probably appears in Science in a few weeks. But they keep talking about quantum supremacy, and I want to tell you what it is. Every week there would be someone talking about that. Every right and wrong, and then well, what is it? And then how do you judge for yourself when quantum supremacy has been achieved or not? So the quantum supremacy, the term was coined by John Preskill from Caltech way before these things happened, and they have this political connotation and with the word supremacy, and then came in. But we try to stick with the word. We put quantum in front of it so not confuse people. But you know, it's not the best, but whatever. There's not much we can do now. But I think quantum supremacy will remain more than all these fluctuations in social behavior. Anyways, so the idea is that you do a computation that is so hard, that is so complicated, that and I get more accurate with these phrases, that cannot be checked with your classical computer. So if I do 9 qubits, like you just saw, we were chasing what we were expecting with our classical computers. If I do 15, then you have to have a bigger computer. If you have 20, your computer starts becoming a supercomputer, and there would be a number at which, and it's few tens of qubits, at which there is no computation power on the face of planet that can be telling you if you have done it right or not. And that is what the idea behind quantum supremacy is. Just showing that some computation can be done and is so complicated that cannot be tested otherwise. It has no usefulness to it at the moment, but it truly, genuinely demonstrates this power of quantum platforms and the power of quantum mechanics to do computation with it. So that is the idea behind it. But as you read these articles and such, I want to equip you with tool to judge these articles and judge the progress of the field properly. To demonstrate quantum complexity, to demonstrate quantum supremacy, you need two ingredients. One is complexity. The computation you are doing has to be complex. It should not be done otherwise. If there is a mean field approximation to it, if DMRG can do it, if you're asking for very simple questions like what is magnetism, there are 1,000 ways of getting there. That is not constitute quantum. The problem has to be complex. And commonly, when the dynamic in a classical system, you have to get these concepts of chaos and integrable to quantum systems. When the dynamics is chaotic, it means that you're exploring the entire Hilbert space available to you, and that is where things start getting hard to compute. But if the system is integrable, there is definitely a shortcut to do it, and you're not doing much. So the complexity criteria is one thing. You have to be sure there is this hierarchy of polynomials that computer scientists are talking. So it's not that it's just your quantum platform is able to do something. It has to do something which make computer scientists happy, and they're very hard people to keep happy. Also, you have to do the operation with high fidelity. There is nothing to be proud of if you cannot do a design of something with high fidelity. Do you know who designed this? You don't know, because they failed. If they didn't fail, you would know who did that. There's no point of doing a low fidelity operation. The DMRG probably can do the same. A good theorist can do a back of envelope computation for something with a rough approximation. You have to have fidelity. The work has to demonstrate fidelity. It's not just about putting a bunch of atoms next to each other. You got to respect these two criteria. In this
beyond the expectations.
Okay, so in the example which I will walk you through next is based on our recent work which we posted on arXiv recently. You see how we do something and we go against these criteria and how we check it against these criteria. And I think I ask you to, whenever you see a manuscript, article, pop article, whatever, Facebook post has this word in it, ask for these criteria, look for these criteria. Okay, we picked up a computation, that is the computation, that is the algorithm we implemented. We got, let's say this is a 5-qubit example of it, so we don't make it messy, just we have gone up to 9, but just for now is 5 qubits. You get 5 qubits, and in these 5 qubits you put 2 photons, or you go to half filling. That's where you want to be. Half of the qubits are filled with photons, and then you turn on your pulses. The pulses in here are, you turn on the coupling between the qubits so qubits see each other, and then you have certain detuning. This is the disorder in the landscape. This is where the qubit, the on-site potential of the qubit is. And then the qubit keeps seeing each other, and then you turn it off. Okay, that's for technical reasons. That's what we chose. And then after doing this Floquet business for several times, or after each of them, you stop and read the state of every qubit. Okay, that is a computation that you can go and do in your classical computer. You put these pulses, and you can predict the output. Okay, so how possibly an output would look like? Okay, we were in the half filling, and we were clever with our dynamic choice to be photon number preserving, meaning that we put n number of photons into our circuit, and at the end there was n number of photons, and anything besides that we could trash. So for 5 qubits and half filling, if you can see down there, these are 10 possible outputs, 10 possible outcomes. And then you repeat the experiment. So this is, you do the 10 cycle. By cycle, I'm referring to one of these guys. You stop right in here after the first interaction pulse, and you do the measurement. and then you do the measurement, and then you repeat and repeat, and then you get after 10 cycles you stop and you measure, and then repeat, and then you form probabilities, and then you come with a different instance of this order, and then you read the probabilities again and again and again. But this is becoming a very humongous data set, and it's just impossible to look at. But the complexity of the algorithm can be even seen in this outcome of these probabilities. This is, if you know, it's called the boson sampling. We were inspired by the idea of boson sampling, meaning that you have a waveguides and path, and you shoot certain photons in this path, and this path interact with each other, and then at the end it's very hard to predict which channel the photon would come out. Imagine you shoot a photon, there are 10 different channels, you know where you're beginning, but these lines are all touching with each other and whatnot, and it's very hard to predict where is it going to come out as a result of quantum interference. It's the same as you shine your plane wave through a frosted glass. You form a laser speckle, like a laser speckle pattern on a wall. It's very high intensity, low intensity. It's very hard to predict the pattern because it very sensitively depends on the length that it travels through the wall, through the distorted media of frosted glass in this case. This is sort of analogous to that, right? We have some disorder landscape. We inject 2 photons as a function of time. These go and then diffuse and then interact and whatnot. And it's just very hard to predict where they come out. And you see it's a very featureful pattern. The fact that it's featureful is what makes it very hard to predict. And that is the essence of the complexity of this algorithm. If it was uniform, you guys could have come up with a reason why it's uniform. The fact that it has up and downs and sensitively depend on the choices of the disorder and the coupling makes it very featureful, and these long things are not coming by accident. You can see the error bars in them. And that is why that's why it's interesting. Okay.
What's different in those 4 instances?
They are different in choices of, you see there's a little offset in here that associated to local disorder, like a different realization of disorder. Or could be the lengths of these guys get a little stretch and whatnot. It's a different Hamiltonian, either different in coupling or different in local potential.
So sorry, you're only showing 2 of the 32 or whatever outputs?
Right.
You're post-selecting on the ones where it worked?
You post-select.
From measuring.
No, you post-select, and then you come in here.
Yeah,
What do you mean work?
Photon loss, you could get 1, 0, 0.
You get 0, yeah, you trash that.
So you post-selected, you threw it away after it happened. But it was.
Well, I'm not selecting to get the only right answer. I'm selecting to right, but okay, the dynamic does not have any microwave lines in here, so right, the photon should be preserved.
Well, just because of T1 and finite temperature, you can get 1, 2, 3, 4, 5.
Yes, and we are trashing that.
Right.
We are selecting that,
Yeah,
but we are not selecting on the correct answer, right? It's still
selecting on the correct number of photons,
Right.
the system doesn't actually respect the real dynamics of your system.
well. The question is how much error I have by doing that. Is this 2% of my data and I'm trashing 98%, or is it 98% is correct and I'm just trashing 2%?
Right, but in terms of your train going out the back window, you're kind of trying to shove the train back in a little bit.
Yes, yeah, there is post-selection. There is error detection, right, of course.
Right, but the sub-ensemble doesn't have the same behavior as the full ensemble. The whole point of weak values, for instance, right, is that the sub-ensemble behaves differently from the full ensemble of outcomes. The full evolution of the system can be very different than the sub-ensemble you select. So how do you know that you're not helping the quantum supremacy by selecting out the,
We are helping it. Of course we are helping it. The question is how much I'm helping it.
Right. So how do you estimate how much you're helping it?
Well, you count how many incidents you trashed.
Oh, you don't calculate the, what would,
No, at the end you make a mistake. You see, this case, you have to have 2 photons, and you have to ask me how many instances I trashed which had more than 2 photons.
what fraction do you throw away?
I think at the level of 9 qubit, maybe I would be 10%. I have to look at the
I guess it depends on the number of cycles also.
Right. And then the question is how many cycles it takes to be chaotic. You go all the way to infinity, yeah, everything is lost and you're doing trash. That the trick with this algorithm is that is cleverly chosen to get to ergodic phase before the coherence take over. That there is some thinking has gone to choice of the algorithm. I can get to it later. But I think at this level, I think maybe for these 5 qubits you're looking at, maybe few percent outcomes are wrong. Not happy. No, we are post-selecting, of course.
If I can't select it, if I can't calculate it, when you get to the supreme version, I just get concerned that.
Oh, you should get concerned. Everybody's concerned. That's very good to be concerned. But the question is, when I was right before supremacy at 48, how much error I was making, and then you can tell me that my extrapolation is going to keep going the way it was, or at 48 and 49 is just day and night different. And that conversation can go forever. Yes, I agree. But the goal is to be so little error that you say, look, I was about 12% error. Now I add 1 more qubit. How bad can I be? That's the goal. That's the idea. But that's the beauty of it, that you cannot ever rule that out. I don't know beauty, but this is what it is. Sure. OK. So very soon, with lots of these instances, you collect lots of probabilities and lots of numbers. How the heck are you going to show these massive sets of data? And then I said I want to explore and show that they are uniformly explore the Hilbert space, and that's a signature of complexity that we are after. So I'm going to trash this part of information that which state showed probability, and show you the probability, the histogram of probabilities, without where it's coming from. I'm going to tell you that, sometimes I get this value. Okay, how many times or what are the instances I got this much value, without paying attention to which state gave that to me, okay? That's a bit simplification here. And this is the probabilities I read, and this is the histogram of them. And you see, usually you read very small numbers, but exponentially going down, you have sometimes reading very tall peaks. And again, that is the signature of this speckle pattern I mentioned. And then you repeat the experiment with more and more qubits. You see more states getting involved in the half-filling of bigger system sizes, and then the probabilities of getting high probabilities going down. However, if you normalize properly and bringing the number of the states that are in that half-filling, multiply that by that probability, now redefining the axis, every data we got fits on top of each other. And you can put an exponential line without any fitting parameter to it. This is a number, this normalized, so it's a number, this is a number. You can put an exponential with 0 fitting in it. And this is this called Porter-Thomas distribution, and it comes where your variables are Gaussian randomly distributed. Then you're uniformly exploring the Hilbert space, and the signature of it is that when you measure this probability, you have exponential decay. And that is a clear indication that we are exploring this Hilbert space uniformly, and there is no shortcut to do this to measure these probabilities unless you really sit down and exponentiate a matrix which has random components to it. So there is nothing you can do about it. Okay. Right. So that's where we are. That's where we with the 9 qubits and whatnot. Right, but what if, right, so post-selection ideas comes in. Oh, I didn't have it. Okay, I think it's after the talk. Okay, okay, so there is a probability distribution we measured, and there is this line. What is the degree of similitude between these two lines? How much this one looks like that one? So you can get, there is some KL convergence or divergence criteria, which tells you how the two curves, the exponential and look like each other. And you can see that it really looked like the measured value versus the exponential, the two curves become very much look like each other after just 2 kicks, 2 cycles. And after that, things really go bad. And that is when the decoherence takes over, and then the system is not really a pure state and a mixed state, and our errors are so much that you're really not having what you claim. So that's the beauty of the algorithm, that you only need 50 or 100 nanoseconds to be somewhere that you're really, really good ergodic, 2 orders of magnitude reduction, and the whole 2 curves are really much look like each other. You have really gone honest to God through your whole system, and you diffuse through whole system, and you really have an ergodic dynamic. So that is checking the 2 curves against each other. So the second thing I said is about fidelity. Right, I have to show that, I put these numbers in here, it's a small system. I have to be showing you that I can do this with high fidelity, and it's not just, some random output. Random output could get close to Gaussian exponential distribution, Porter-Thomas. But I have to show you whatever I had in mind, whatever I set the computers, the quantum computer to do, is what I'm really getting in the lab. So this is as a number of cycles. Even in spite of that post-selection, you see that the control error and the phasing error makes you the fidelity to go low. This is some measure of fidelity. If you're 1, meaning that what you had in mind and the probabilities that you got is really matching, that's perfect. And when it gets to random guess, I think this is 0, right? If you would randomly guess the output, you get 0. And you can see how better we are, how much you have to trust us. And at some point, if this was coming down that much, you say, well, I don't need you. I could have randomly guessed the output. You're not better than the random output. 5 qubits, that's the error per cycle. And remember, we only need 2 cycles. And then you continue this business. You make your quantum system larger. You make more errors. The error comes down faster. At 9 qubits, you're making about 3% error per cycle. OK, that's the number we have now. It's interesting to see how this compares to where we want to be at the number of qubits that would show supremacy. If you look at these, like how roughly the error is per qubit per cycle, you get something about 0.35 error per qubit per cycle, and we need 2 cycles to get to this ergodic phase. So we have about 0.7% error per qubit. That's the error we have, that all of these are kind of roughly pointing to the same number. OK, how many of these we need to show supremacy? If we have, let's say, 70 qubits, and I said it's ergodic, so you need the whole wave vector to know the state of the system. You need about 1 million petabyte. I have no idea what that means, but I think it's a large number. OK, it says 1 million times more powerful. OK, so that's what it is. So you can be sure that, forget about computational complexity. There is no computer on the face of the planet at the moment to store this wave vector, let alone to evolve it forward in time. And that's where we want to be. So you make 70 qubits, you raise this number to the power of 70, I think, and then you get 49% error. So we can predict, if this is all stay together intact, we can predict the output with 49% fidelity. We are here, and then random guess would be here. So you might be wanting to trust us. I think you guys trust Google anyway, so we just another. OK, so this is where we are with this business, and that's where we are going with this. OK. OK, I think I'm doing fine in time. Right, I think I'm OK. OK, so I don't want to tell you, besides this supremacy idea, what condensed matter physicists think this is getting interesting, or what is people who work on these condensed matter system on daily basis, what would they tell you that can be done with qubits, and how many qubits it takes? Imagine you have good control over the qubits, like at the control level I showed, but you maintain it in a larger system, and you have coherence, and you might choose to have some post-selection techniques and do some error detection. So I picked 4 of my favorite theories. I emailed them and say, hey, how many qubits it takes to do something interesting, and what that interesting thing would be. And this is the answer I received from them. And look at the numbers they are saying. These guys work with these things on a daily basis. OK, Chetan is off, but I explain why Chetan is off. And then they're pointing to very diverse sets of problems. So if you could make a few tens of qubits, and you really become master of control of the qubits. And then there's lots of problems that you can answer if you start thinking outside the box of Shor algorithm and RSA encryption and whatnot. There's many things to do in the field of condensed matter, non-equilibrium dynamic, and even some problems that we have been ignored and they stay there intact, and we just don't pay attention to them, like fluid dynamics. So this 100 comes that if you really look into the ground state of the system, there are tricks to get the ground state of a Hamiltonian, so you can go slightly bigger. But if you think about the dynamic in a system as these two examples demonstrated, then the 20 whatever is the limit that you can go to. So the horizon is not that far. We can really do something cool probably in the near future. That's really encouraging us, and that makes us to wake up every day and go to the lab and work hard, because it's not that far. Hopefully we can hit that soon. Okay, this is the team who made the work possible. Lots of experimental people in this group. And then there is a theory team in Los Angeles supporting all the efforts. The butterfly effort was done in collaboration with Dimitris Anglikis' team at the National University of Singapore. Right, so lots of people are focusing on the infrastructure, fabrication, electronics. That's why the whole thing's, that's how the whole thing operates, and we are very happy, big family. So this is my manager, and then if you met him or you know him, he's a bit vague and he's not very explicit. So he says things that you cannot question. He says, we need to double, and then he said that a few years ago we had no idea what he has in mind, and we never dared to ask what the heck he had in his mind. So what do? We talk among ourselves. What should we do? We took some action, and then we say, okay, here this is what we're thinking. And we took back the result to him. The experiment was not done in the lab. But we back to him, and he was like, no, this is not what I meant. You have to double the number of qubits. So that was the missing phrase. So from 2013, we did these works, and this is what is in your hand, and that's what we are doing these days. There are 15 qubits. I want to, and then we have more in the lab at the moment. But as promised, we are going to stay in the top of the control of the system, and we are going to have, whenever we make it bigger, we are not sacrificing controllability or coherence. These chips nowadays are made by the idea of flip chip, meaning that you put your qubits in one chip and you bring the wires from the top layer or bottom layer, and that's how you can really overcome the topological barrier of getting to the middle qubits in a 2D land. And to assure you this is real, this is a data on it characterizing it, so it's really exists in the lab and is in the fridge at the moment. Okay. Final word. At Google, we are smart in a sense that we are certain we are not able to make the quantum computer ourselves. We know that much about ourselves. And we are really understanding this has to be a community effort. And the whole quantum technology community and quantum algorithm people has to all work together to make this happen. This is not something 30 people can close the door and make it. And to reach the community, we have start working on various approaches to engage the community. And I can go over these. It would take 20 minutes each item. But I can talk to you later or via email or something. But these are not just things we wrote. There is lots of effort behind each item to get this community involvement going. We think we all have to work together. Next time you are in Santa Barbara at KITP, just come and stop by our lab, and we can show you around. We can talk about these items, and then we can move forward from there. Thank you. I can touch this one and mess it up.
Okay, do we have questions?
Well, I have a very
simple question. I mean, how do you know, with all these different approaches that people take to these to these quantum computers, is there sort of a standard problem that everybody says, if we can solve that in a given short time, that's the holy grail? I mean,
so the holy grail was Shor's algorithm and Grover's search, but those are really hard. That's this idea of supremacy became a low-hanging fruit, and that's why I'm insisting on defining it properly, so no one take advantage of the ambiguity and claim it before we can claim it, because we want to do it right. But I think this supremacy is growing. But also my point is that we can work together on ideas, and see, we can start working on these and making them well defined and making a tangible target. Essentially, these are theorists who do these things on a daily basis, and they get stuck when they go beyond this number of qubits. But it's not the standard of the community yet. But you can imagine dynamic in a non-equilibrium dynamic is hard. But nothing has the celebrated position of Shor's algorithm, and now supremacy is gaining some attention.
Other questions?
and you showed a graph very early on that said, with quantum computing, it keeps going up and up and up, and the standard computing goes up and then comes back down.
No. Let me show that again.
I don't.
No. I didn't. No, this was meant to.
Yeah, that one there, upper left.
Yes. No, by that I mean that this is a recipe to how behave in the lab. In the lab, an experimentalist should behave this way. When they make a bigger system, it should keep in mind the controllability and goes up straight. If you don't control, you get to some land that condensed matter people have been many years ago. You're not doing much favor. I'm saying this is a recipe for action. This is, yeah.
Okay.
How good those oscillator has to be before they can be sort of
How-
qualify the qubit? How good are those quality factors?
Quality factor are about a million or so.
Like
Q factor is about a million. Yeah.
So it's not enormous, right? Like a million sometimes. It's not,
Some people have a few million or so, yeah.
it's not difficult to achieve.
Yeah.
Are you under pressure to sell products?
Right. There is another aspect of the business, which is some other companies start to offer access to their platform. And we are thinking also to make fridges and maintain it and provide access for people to log in and make their own butterflies, could be a dragonfly or something. You can log in and then do things yourself. So we are thinking along those lines. The exact format of it would be unfold in the next few years or near future.
Besides the actual quantum chip, I guess another issue would be, and that depends very much on the algorithm you want to use, but for some algorithms, I suppose it could be, also very complicated to get your initial state in and to measure your final state and get the information out that you want, right? So is that, where a lot of work is happening right now, or not?
Not sure if I fully. So I'm focusing on a start.
For example, you showed you had a very simple ingoing state, right? You had 5 qubits. You just
right,
put photons into 2 of the qubits, and then you saw what happened. But for certain problems, right, including Shor's algorithm, I suppose the initial state would be much more complicated, right?
But you can get to that, what you call initial state, from another protocol, which starts from a very trivial state. So at this moment, maybe theorists are thinking about that, but in the lab, no, there's not much thinking we just try to make better qubits and larger number of qubits.
But
Maybe,
all this is done on chip, right? Initialization of qubits is on the same chip. Readout of qubits
right.
is on the same chip.
Yes, yes. But
Part of the chip.
But they're not really different, because if you can do a projective measurement, then you know what state you're in, right? So preparation of an initial state and measurement of the final state are kind of the same operation. You just measure the states. If you don't like them,
Yeah,
you
no,
form
of
some
course, I
expectations
mean,
you love
preparation
them.
and measurement is the same problem, I
But the
know.
usual thing you start with is a separable state. Like the
Is
quantum computer entangles as you go along, but you think of it as starting separable, ending separable, and
But then I'm limiting myself very much in the kind of algorithms I can explore, right? If I
no,
start with
because like he
several
said,
states.
the generation of the entanglement is part of the algorithm.
Yeah, okay.
well, like it or not, you leave the system, it's just going to be on 0, 0, 0, 0. And then in making a product state is easy. And then if you want an entangled state, you got to put a protocol in there to get there. And you can call that now initial state.
You sort of dismissed Shor's algorithm by saying it's hard. Why is it harder than any of these things?
It takes lots of operation, lots of gates. Which probably you have seen something on experiment, but they're a very contrived version of it. If you do honest to God, it would be very, very long, and we ran out of coherence of the system, or the errors accumulate, and there's no chance of it. So the current technologies, I don't think are at the level to demonstrate Shor algorithm.
Does there need to be special quantum software developed to?
I don't know, but what do you mean by quantum software?
Well, I guess one just to control the hardware.
Oh, the software which communicate, right. There is many of my colleagues are in that business of controlling and talking. Well, control comes to two aspects. One is just write the code, and other is what codes to write and some knowledge of the physics of the problem and what happens and optimization. Yes, this is in fact where most of our effort and energy goes. And then you get that software and the control managed, then the results follow easily.
Okay, let's stop here. Thank you very much.
Sure.